My name is Jay. I'm from Google Research. And as we all know, simulation is a very powerful tool in robot learning. But the sim-to-real gap is a bottleneck that prevents us to fully tap into the power of simulations. In this tutorial, Dr. Fabio Ramos is going to tell us different ways to overcome this sim-to-real gap. Dr. Fabio Ramos is a professor in robotics and machine learning at the University of Sydney. He is also a principal research scientist at NVIDIA. His research focuses on stochastic machine learning technique for large-scale Bayesian inference and decision-making with applications in robotics, mining, environmental monitoring, and healthcare. Between 2008 and 2011, he has led the team that designed the first open-pit autonomous iron mine in the world. He has published over 150 peer-reviewed papers and won all kinds of awards, including Best Paper Awards in many top-tier conferences. Without further ado, please take it away. Thanks.
All right, I hope you can hear me okay. Yeah, excellent. Thank you so much for the introduction. Great pleasure to be here. Thanks for the invitation. And thanks for sticking around. Finally, the weather is good and you could be at the beach instead of being here, right? So I really appreciate your presence. So let me start by telling you a bit of a story here. So this is back in 2008, so 2008. A large mining company came to us and said, look, guys, I have some problem. I have a problem. I want you to automate this mine. And the mine is right there, right? It was called West Angeles. It's in this region in the north west of Australia. There's not much around there apart from these beautiful rocks. And we said, okay, let's do that. How does that work, right? Well, what's the process in there? And the way it works is in iron ore mining, you need to drill the ground. And after you drill lots of these holes, you fill it up with explosives and fire 200 of those holes together, almost together, to generate a shock wave, break the rocks. And then with the broken rocks, you have an excavator that moves these rocks to the trucks and then so on, all the way to the pit where they are exported. And the very first piece of equipment we decided to automate was this one. This is a drill. Okay, so you press a button, the drill needs to drill in the right spot. And that's the very first time that we interact with our product. Our product in this case are the rocks, the beautiful rocks that contain a lot of iron. This was the most important part of the automation process, which we only figure out later on in the overall picture, because it's the piece of equipment that give us the most information content all over the automation process. Well, how did we start automating this stuff? Well, the first thing we did was designing a simulator for it. Because with simulators, we can actually have a much better understanding of what goes on. And here you see our drill simulator. It wasn't a super accurate simulator, but it gave us enough to reason about the problem. You see how the drill interfaces with the geological layers and so on. Okay, what can we do next? Okay, we got the drill done. We collect information. We have that simulated. The next piece of equipment, okay, is this toy there. So that's a truck. It weighs about 200 tons and carries about 200 tons. And we decided, okay, let's take this truck, download the latest model from CVPR for object detection, train on Caltech 101 at that time, right? And test it, see if we can do object detection and recognition in there, right? What could go wrong, right? So and this is some of the tests we done in the process. All right, so that's my dirty laundry right here for you. Well, after a bit of you know, a few tests and more experiments, and fast forward maybe a decade or so, here's how this this area looks like right now. So that's the area in the north west of Australia, our drills. You still have humans in the loop, but all these trucks are now autonomous, right? So we have about 100, 200 of these trucks in different mines, all carrying quite a lot of minerals from one place to the next. One way we managed to automate the entire process was essentially removing humans from that region, right? So when you saw that picture there that says, you know, autonomous mining, that means if someone entered the mine, we will stop everything because we just didn't have enough simulation capabilities to handle all of that. And redundancy was quite important, as was simulation. And you see some of the simulated and real. But even more than automating these big pieces of equipment was looking at the big picture, looking at the entire mine. So here is the control area where you can simulate how these big pieces of equipment interact with the ground. You can estimate the production levels, how much mineral and what quality will be shipped to the customer. So let me tell you a few of the messages and lessons I learned through this process. First thing is that automating 200-ton machines is super fun. And is even more fun when I see other roboticists, and I can always tell them that my robot is bigger than theirs, right? And simulation was a critical component for the entire process, right? From designing to engineering to the different components of the automation process, even to talk to other companies, the OEMs that we were working with us in putting this together. Now, the other major component was that, well, we actually need to understand the uncertainty over the entire process and how wrong things could go, as you saw at the beginning. So redundancy and modeling uncertainty were very important. And finally, something that we learned later on is that usually companies go to you and ask you to automate a truck or something. But actually what they mean, they want an automated process. So it's always important to contextualize your robot in the sense of you know, the equipment and everything that is around as an entire system, entire process. Okay, with that in mind, with these lessons, I want to give you this brief tutorial on how to think about simulations, how to adapt simulations to the real world, and some of the research opportunities I see in the area for us in the future. So let's start with robotic simulation. That's a brief overview of the history of simulation in robotics. You might remember Gazebo, right? I was doing my PhD. The Gazebo was the tool if I wanted to do a simulation, and still going, right? Gazebo is still going. You can still download and use it. A major development was Mujoko, right? With all these beautiful contexts and the work of the Emo put into this, Mujoko really sped up a lot of the developments in simulator and inspire many of the next simulators. Companies started being created, VRAP, which made simulation much easier, and other companies could use VRAP to automate the process. So you're not just looking at one automation procedure, but systems. Well, and then Irving and others, right, expand that and say, let's create PyBullet and make an open source version of it, which was beautiful. Later on, NVIDIA decided, okay, maybe we should also get into simulation because, well, we could do simulation in different kinds of hardware, not just CPU. And then Isaac Jim was created and released about that time. 19, and you probably have seen quite a few talks on Isaac Jim and how we use Isaac Jim for training. More recently, there is a new simulator. In fact, the latest version of this simulator was released today here, which is yesterday in the US, right? It's the Isaac Sim. A lot of people ask me, what's the difference between GIM and SIM? Well, SIM is a superset of GIM. So it's got GIM, but got rendering, real trace rendering, plus a lot of control in it, RMPs and so on. So it's a lot of things going in Isaac Sim. But what I actually find something really interesting and a development for the future is this idea that we can now create languages that allow you to code your simulator in a very efficient way. So if you use PyTorch for your neural network stuff, you know that PyTorch is tensor-centric. So it cares about the tensor manipulation of high dimensional tensors. These languages here are kernel-centric. They care about being effective in kernels in CUDA, and they are differentiable in the sense that they have auto-diff. But you can code your own simulator, and after you put the equations and programming there, you can deploy into the rendering and the rest of the simulation pipeline. So I actually think that the development of this probabilistic, differentiable programming languages will be quite impactful here and into the future. All right, so what's the next frontier in terms of automation and robotic simulation? Well, if we are simulating a robot, we'd like to now simulate the entire factory, where we go from a single robot, multiple realizations of that robot in the factory, and different configurations of that. So we are looking not just one machine, but simulating the entire system. And you can randomize over all of these different scenarios to be more robust, to address the problem of sim to real, and so on. So let's talk about sim to real now, and how can we use these simulators to actually help us in deploying all of these systems. But you might ask this question, what if the simulation is different to the real world? And then if the simulation is different to the real world, how can you better do decision-making in that? So based on this, we started looking at what is actually involved in the process of capturing the uncertainty of the physical world inside our simulator. So I like to say all simulators are wrong, some are useful. So imagine the following problem. I have my simulator here, could be any simulator. And it's a simulator that I might not even know the equations. I just know some of the variables, the physical variables that they use to actually simulate a process. If I plug some values, let's say masses, friction, and so on, and press a button, the simulator will do what is called forward modeling, okay? We'll generate trajectories from that. And that will give us a simulator behavior. Well, now that we have a simulator behavior, we can look at the real world and see the real behavior. Here's the tricky bit. If we have the real behavior, how do we go back to the simulator and ask the question? Well, what is the value of these physical variables, the parameters of your simulator, that actually give me a simulation that corresponds to the real world? So if you did physics, or if you, even in biology, this process is called inverse modeling. We are going from a large, trajectory, high dimensional data, to then try to infer physical properties behind it. And that process is usually non-unique. Remember in the tutorial yesterday, planning is also non-unique. And one way to handle about non-uniqueness is to think about solutions as not argmax point solutions, but actually think about solutions as sets. And because we think about solutions as sets, there is a theory that helps us to understand these things. So how to adapt simulation to reflect the real world, and including this notion of sets, the sets that corresponds to the possible physical values of the variables in the simulation. That's why we want to connect simulators with probabilistic inference. This is a tutorial on simulation, but probabilistic inference is very important. You've seen this equation before, I'm pretty sure, but let's just clarify a few items in the terminology here. So that equation is perhaps one of the most interesting ones ever proposed, because allow you to reason about knowledge that you know before you see any piece of data with the knowledge you get when you see data. So if you don't see any data, you have an opportunity to add knowledge in there, and that happens through the definition of this quantity called a prior. Once you observe some data, big D here, you can potentially compute something called a likelihood function, which tells us how much the data agree with the model you have behind. The stuff in the denominator is the tricky bit. That's the marginal likelihood. It's got this integral in there, difficult to compute. And that's why we have so much research in probabilistic inference. And if you can do that, you can then reason about the posterior, which combines prior information with the data. So different sources of knowledge being combined in a single equation. All right. How do we connect then our simulator in here and look into this problem from a probabilistic perspective? And I'm going to discuss 3 cases here. The first one is I have my simulator. I don't know the equations. I just know the parameters it has, and I don't know the solvers. These are all kind of hidden from me. And the simulator might even be quite expensive. So how do you do inference in this case? So a few years ago, we proposed something called Bayesian, which is a strategy to compute distribution over physical parameters from a simulator given reality. So this is how it works, right? So suppose that you have some prior knowledge on how physical parameters should be. So let's say mass, you know, the mass is non-negative, you put a prior distribution in it. And you plug this, you sample that, and you run your simulator with different values of mass of that parameter. So you're going to have quite a few simulation results, okay? You plug this prior, so values of mass, trajectories, they were all generated in simulations through forward modeling. And then you plug real data in it. And you ask the question to Bayesian, what is the posterior of these parameters given the real data? And that's what this method will give you. It will give you a posterior. So you see the prior, you see the posterior in there. It might be multimodal. And that combines the prior information with the real trajectory and gives you a distribution over those. And that happens through an approximation to the Bayesian equation that I showed you just before. And that is based on, you know, learning this density estimator Q function that essentially estimate a distribution over theta given a real trajectory. Let's look inside Bayesian just for a bit and see what we can do with that. And then I'll show you some examples to see how that applies to your own work. So here's a time series, and here's some images, for example, right? All generated from a simulation or reality. We assume that reality will also give you time series and images. The next step is we can extract some features out of these trajectories or images. You can use the latest tool out there, you know, diffusion, transformers with nerve features, whatever. Or you can come up with normalized cross correlations and means and everything else. And we call this summary statistics, okay? So they summarize the trajectories one way or another. From this summary statistics, we can learn a density estimator that could be, for example, random Fourier features, a regression model, or could be MLP. And connect that to something that estimates the density, but in a multimodal kind of sense. So for example, it could be normalizing flows. So that worked from Fabio Muratori, or a mixture of Gaussian, for example. So that's the posterior you have. But what is quite interesting is that if you have a posterior, you can then try to train a policy on this posterior. And one way of doing it is through domain randomization. So domain randomization was proposed in 2017 as an idea of averaging over different realizations of reality and learning a policy by optimizing this function J. But usually this was done over the prior. But the prior might be way too broad for you, so it lead to a lot of instabilities. if you randomize according to the posterior, you actually get much better performance in your policy and much better conversion to the much better chance to perform well in the real world. So let's see some examples here. So that's the work that Caroline Matthew did with us. And the idea is I'm pouring granular material, right, through with this robot through a cup. And I need to estimate properties, mechanical properties of this granular material. So, you know, this could be rolling, friction, and things like that. So following the basing procedure, we extract, so this is 1 grain of that. We extract summary statistics out of this, and actually we only require pictures of the realization of the process, right? So these rings that were pouring there after we put the grains into this funnel give us a pretty good indication already of rolling and restitution parameters that we are after. So after we sample, right, different values for rolling, friction, restitution, and so on, we learn this this model and do domain randomization to estimate a policy. Okay, so now you can see that these are results of the simulation, and the policy here is quite simple. It is to pour the granular material through this funnel at different heights to achieve a particular pattern, right? And that pattern is this kind of concentric rings, as you've seen there. So if you get correct physical parameters, this thing can actually perform pretty decently, as you see in simulation and in the real world. Okay, extending that, right? And what is actually very interesting is that you know, to do things to real, you don't need a super accurate sensor to estimate trajectories. This other work, we actually use sound to estimate a trajectory of a ball bouncing in different surfaces. Depending on the parameters, the physical parameters of that, the ball will bounce differently. And what is also interesting is that the process of bouncing is stochastic, because there's a lot of stochasticity in the surface of that ball. So we want to train a stochastic simulator. It's a simulator that, if you run it multiple times, you give you different realizations, and you capture the different types of bouncing. So what you see here is after we train the posterior, which now estimates the noise of the bouncing process, we can learn a policy. You see reality, you see real for different types of balls, including this moon ball, which has a lot of stochasticity in the way it bounces. And we can close the sync to real result, also bouncing on an edge in there, and see if the ball bounces back inside the cup as we would expect. Okay, all of that just from sound. Okay, that's what we use to estimate the trajectories of this this process. You can also train a policy to track the position of the ball and use the arm to bounce it back to where we are. Okay, so that's interesting. We can estimate some parameters of the physical process, but what if we could go back to reality a few times? And that's one of the idea, right? So we are doing sim, we train a policy, we run the policy in the real world, we update the posterior with new observations, and then we do the real to sim, and we can go back to this process. We can redo it multiple times. So what happens when you do that? So let's say a simple example here. You have your policy there. It's trained on the prior. So maybe you have all kinds of instabilities, and you see that from the noise in there. This is the posterior, right? Over the parameters, you know, length and mass pull. And we keep on going back to reality, re-estimating the posterior, and carry on in this way. As the policy gets better, the posterior gets better, and the performance in real life gets better. And that's a very interesting process. If we can afford going back to reality, you can gain a lot from this. That's an example where we had a little skid steer robot going around on a carpet, and we didn't know it's really hard to estimate friction on the carpet. But as we go back, collect new data, simulate the data, and then eventually even change the surface, and in real time, re-estimate the policy to get the right behavior we expect, which we'll see in a minute here. Let's see, right there. All right, so if you change the surface, you can easily recompute the parameters of friction to get the desired behavior. And that happens as well when you look at the plot from the top. These kind of ideas were used by Fabio Muratori in this paper, the paper he presented here in last year, where you are looking at this fruit pendulum. This is trained on prior, so not that great. Then after the first iteration, you go back, re-estimate the procedure, not that great, and keep going. Iteration 2, 3, it gets much better, and 4, where you can actually balance the system pretty accurately, right? So the message here is we can do pretty well if you can afford going back to reality, to the real world a few times. Okay, but all this work I mentioned, the number of variables we actually try to infer were kind of limited, right? So, maybe between 5 to 10 variables is what we could do. It's the most difficult problem when you don't have access to equations. But what if we know more about our system? And what if we can take derivatives out of the equations, the simulation equations? So that's the case number 2 for us here. Because if we do know the equations, and if we can take derivatives of the equation, you can write a likelihood function. And a likelihood function can be something as simple as the difference between simulation trajectory, which is generated from simulation parameters, collecting a data set of trajectories in real and sim, specifying a loss, so let's say a least square loss kind of thing, and putting that into an exponential equation to give you a likelihood function. If everything is differentiable, we can do a lot. And what is even more interesting, we can connect to the folks doing statistics and doing probabilistic inference, where the goal is always the top right in your screen right there, where we want probabilistic inference methods that are more general, so we don't actually have to derive lower bounds, but also fast. And there's been a lot of interesting developments in probabilistic inference. So let me give you an example of how this thing can be useful for us. So this idea was, let's try to make a cutting process through a finite element method differentiable, right? That's the work from Eric Hayden right there. So he created a new simulator, which is based on damage mechanics, to simulate cutting. And he made that differentiable, believe it or not, right? Cutting is something that I will never believe it would be differentiable, but it's a good approximation. So from the forces we exert on the knife, we try to estimate the parameters of that potato, right? Of this fruit. So the way it happens is it's a finite element method. So you need a mesh. You need a mesh, and you put the equations in there, which essentially crack propagation through a spring type of model. And suppose that you know where you're going to cut, you create copies of that mesh locally. And you can then start your process of cutting and simulating at the same time. You see, as the springs get stretched, eventually they disappear. And let's open our potato here. Get the links, connecting one end to the other. This is the mesh inside the potato, which we can adapt through optimal transport to different kinds of potatoes. And then you see inside the result of the finite element simulating all of these processes that you see in there. Now, because everything is differentiable, and I can write down a likelihood function, I can also use something like Adam. And you see here the ground truth force profile as I was cutting, and the estimated force profile while we were simulating the process, and how quickly we can match these two things. That will give us a point estimate. But the whole point of this tutorial is to never do point estimate. It's to actually look at distributions. So how do you compute a distribution of physical parameters if we have gradient? One of the most interesting developments is this thing called stochastic gradient Langevin dynamics inference that actually won the time of the 10-year kind of award at ICML last year. It's a beautiful MCMC algorithm, and what it does is it connects optimization. So you see this little particle going around trying to find the minimum of that function, but also bounces. So there's a little bit of noise in there. It's a beautiful algorithm because it connects gradient optimization with sampling. And after you wait a little bit for this process, for this particle to stabilize around that, you're always going to be bouncing. You can collect the last particles, and that will give you a non-parametric estimation of your posterior. Right? So Langevin dynamics is a non-parametric estimator. It has an equation that looks like this. All I want you to see in here is that, well, you have the gradient and you have some noise. This noise is added to the process through here. Okay, that's the noise I'm adding to the gradient. And I keep on moving this way. It's just the amount of noise gets reduced as I keep going. And if you ever heard of something called diffusion process, that's based on this idea. Okay, that's a diffusion process right there, but from an MCMC procedure. All right, so then we can do our cutting. And now we cut. While we cut our cucumbers and apples, we can also infer variables of them, whether they are ready to eat or not. The robot can tell just by cutting them. And these are the posteriors computed from our MCMC procedure. Okay, so what if I really want to scale now? Okay, so I want hundreds, perhaps thousands of variables, and we're going to go to case number 3. Now the simulation, I'm assuming the simulation is fast, is differentiable, and I can do hundreds, if not thousands of simulations in parallel. And we need a new algorithm for it, because as you saw in the previous slide, MCMC was one at a time, one chain at a time. I need something parallel. And I need parallel simulators. And as you see here, I mentioned this language called WARP. It's a language that allows you to write differentiable simulators and run them in parallel. So that's something we can use in here. But any differentiable simulator that I can run in parallel will be sufficient for us. So what kind of algorithm can we use that leverages parallelism, leverages differentiability, and is fast enough for us to use in our problem? And one of these algorithms, and perhaps the most interesting one, is this one called STEIN variational gradient descent. You must have heard of variational inference at one point in this conference. There's a lot of VIEs and things like that here. This is another type of variational inference, and it's a non-parametric one. So it can handle non-Gaussian distributions. I don't pick up a variational family like a Gaussian distribution. Exploits differentiability, and it runs in parallel. So suppose that what you see here in this bunch of points, right? Each point is a simulator and running parallel, okay? And each one is telling me this is the length and this is the mass of, let's say, a pendulum problem right there. I update all of these particles in parallel. So each simulator is changing its own value, following the gradient. And eventually all the simulators will kind of reproduce a shape. And that shape is your posterior distribution over the variables you are interested in. Okay, which has this kind of banana shape in there. it's a super interesting algorithm, right? And it was derived from something in statistics that people use a lot of time to prove things, but not very useful from an algorithmic perspective. So the STEIN gradient descent, I won't get into too much detail of that, but it has two main components. One component is a gradient that pushes all the particles down the chain, down the line. And one second component, which is called repulsive force, that makes sure that two particles don't get too close together. There is some kind of force that keep them apart and allow us to capture posterior inference in there. You see, if I run it and trying to capture this trimodal distribution here, the particles never collapse. And that's a super cool algorithm if we want to do optimization in parallel, because avoids mode collapses and things like that. Okay, so you can also add priors, and you see here, if I have a density function in there, I also have the prior, and the prior is this green area here. All the particles need to capture the posterior inside that, and how quickly it converges to the real posterior. Applying that to a real system, we can find the posteriors over this double pendulum, as you're seeing there, the different posteriors and the different methods in there. Or you can also infer the position of these weights inside the box. So that's an underactuated mechanism. You keep on moving, collecting speeds and acceleration, and that will give you a very bimodal distribution in there, but something you can do very quickly with this method. All right, so just to summarize very quickly, I show you three cases of sim-to-real adaptation with probabilistic in the loop. The first case, I didn't know the equations of the simulator, so it's the most general and I could apply to anything. The second case, I knew the equations and I assumed we could take derivatives, gradients of the simulator with respect to the parameters we try to infer. Case number three, we add the fact that we have parallelism in simulation process to scale to more variables. So now I'm going to go very quickly to a couple of research opportunities that I think would be interesting to quite a few of you. So the first one is simulating and representing deformable objects. Well, we need to bring the deformable objects to our simulators. And this is work that done by Rika, where we actually need a way to specify the state of a deformable object. And there is an interesting theory that allow you to specify a shape, a distribution from points. And these points can be embedded in a Hilbert space, as you're seeing there. So here's the idea. You run a key feature extractor from a deformable object. We interpret each of these points as, let's say, a sample from a distribution. The samples are embedded on the Hilbert space through a relatively simple operation. And then you can build your neural network on top. And if you do this, you have you can do Bayesian essentially on this, right? So it's embedding a distribution through samples in a neural net to allow us to represent a deformable object. So representation for deformable objects is a pretty interesting idea for us. The second one is accelerating simulation. And you might have seen this earlier in the year in RSS, the work done by Yash and colleagues on factory. The idea here is, well, we want to simulate highly, problems with a large number of contacts going on between a nut and a bolt. Things are super difficult to do in practice, but you can store a lot of these contacts a priori and come up with summaries of that. In this way, we can simulate in real time hundreds of nuts and bolts in there as an example, right? And then do inference for sim-to-real. So speeding up contact computation is a major area for us. The second one is, well, let's say that the equations, the finite element equations are difficult, slow. One way to do that is to learn a finite element solver, for example, and that could be done by using a graph neural net. So a graph neural net operates on a mesh. A mesh is perhaps the same as the finite element method. You solve the finite element method a few times, and then you create this replica of the entire simulator, which is differentiable. And since it is differentiable, you can use it to, let's say, grasp a strawberry or kiwi, and such that when you grasp, you try to minimize, let's say, the stress on that strawberry or kiwi, or you might also try to maximize the stress and so on. So now we have a differentiable way to interact with objects, assessing the stress and maximizing over quantities that we didn't know. Okay, finally, policy learning. Again, I have a differentiable simulator. I have, and I can do that in parallel. But just having differentiability for policy learning is not sufficient, because, you know, you might have explosion of gradients. They might collapse to something very small. So in this particular work, we split the trajectory into little chunks, making sure they are connected, but we simulate each of these chunks in parallel and average over different windows of the past trajectory. And we use, obviously, the knowledge of the simulation, right, of the problem we are after, implementing one of those languages. Now, what is really interesting when you do this is that you go from a gradient that looks like this. So theta in this case is, let's say, the weight of a neural net that I'm trying to learn, right, the policy. So we go from something that at the left to something that is nice and smooth to the right. And everything is parallel. Someone did a 2-minute video out of this, so check it out. They are quite exciting in showing this stuff. But this last example of the walker is a 152-dimensional policy that needs to be learned on this differentiable system. And that's really hard to do unless you know the equations and are able to simulate things in parallel. Okay, so before I open for questions, I want to give you a few take-home messages. With powerful simulators, robots can learn to make decisions in simulation before being deployed to the real world. Probabilistic inference is a glue that allows the quantification of uncertainty and do better scene to real to scene translation. Differentiable simulators help us to scale this to lots, you know, hundreds of variables. Parallel differential simulation is an exciting new development for policy learning as well. And there are many research opportunities in the real to scene to real to scene and so on. And I think you should join us in this journey. There is this super good paper that Fabio wrote on robot learning for randomized simulation, our review, where he goes over a lot of the literature in the area. I thank my collaborators, and I'm looking forward to your questions. Thank you.
Thank you very much, Fabio. It's a fantastic talk. Any question from audience?
Hello. Thank you, Fabio. Really cool stuff. So it's great to see system identification taken to these great new heights. But I still worry that the hardest part of it is not being addressed, meaning that, you know, once I build a robot model and a model of my environment and a model of, let's say, a funnel and some grains, yes, then I can identify some important physical properties. But it seems to me that the hard part is building all of that stuff in the first place. And if a robot encounters a new scenario, like a new kitchen or a cluttered table, who's going to build that simulation model? So I was wondering if you had any ideas about how to automate that process.
Yeah, great question. So one thing we are trying to do at the moment is randomize over environments, right? So we are working on building randomized kitchens. You saw in the factory there early at the beginning that with some constraints on the type of environments we have, we can randomize over positions. And we can randomize over the amount of material in the warehouse and so on. So randomization is a major tool. We release a tool for this. It's called the replicator. It's part of Isaac Sim. and allow it to do some of this randomization, right? I think we are at the beginning of this process. I don't think we have a final answer. Another interesting thing is you can randomize over texture, over backgrounds, and train better visual estimators and things like that.
Yeah, so I think that that's really useful, but I'm more worried about the inverse problem for that. Like I encounter this actual kitchen and I need to kind of identify this kitchen in my simulator, meaning build a simulation out of it. It's doubtful that I'll get that by randomly sampling, right? I'll need some more structured way to build it.
Yeah, so one interesting aspect, the kitchen we're using there, we got the assets from IKEA, right? So someone was providing the asset to us. The manufacturer of that kitchen was given the assets. And it was relatively easy to then just look at the signals. What I find interesting also is that sometimes you don't need a super accurate measurement geometry to do relatively well in there, right? So this was the idea behind that sound estimation problem. I didn't know about the shape of the table and other things. We still have some relationship to real, which was useful to bring that back into the simulator to try to solve the inverse problem. But I don't have a better answer unless to tell you that we should randomize as much as we can, and randomize over posteriors, such that the process always get more informative as we carry on and add more assets into the process.
Thank you.
Thank you.
Thank you very much for your talk. So I was wondering, I'm trying to understand, like, what are the current frontiers of what you can simulate? So you talked about simulating things like deformable, then things like, you know, factory bolts and stuff. But I'm wondering, like, what are some of the things that you think can't be readily simulated right now, but you think could be achieved in the next few years? Like, I didn't quite get a sense of that from the talk, but what do you feel like is the next thing you want to simulate? Is it like a lot of interaction between objects, or you know, I'm just curious what you think of that.
Yeah. So I think we want to be clear here, because, you know, in my opinion, if we try to simulate everything to the most possible accuracy, we're going to get stuck. So we want simulators that are good enough to the task we want at hand. I don't need to solve Navier-Stokes equations if I don't have to. I'm better do particle simulations out of this. Between the projects and the things I've seen, what I find more interesting is certainly deformable objects, things like food, liquids, all this, that kind of deformable and interaction of deformable object with solids is a pretty interesting area for us. So I would classify that as the first one. The second one is I'm interested in biological materials, going to, you know, agriculture areas, and we're looking at soil, trees, things that move with nature, because I think robots in agriculture, as we saw with the talk here, is a wonderful application area for us. So I'll put this as the two main areas.
All right, thank you.
Hey, Fabio, thanks for the great talk. And directly follow up what you just said for agricultural environments or more unstructured environments. Also, when we go back to your mining example, how can we set up simulators that just not simulate one vegetable, but like the whole environment, that we deploy a robot into these, say, unstructured environments, they automatically build the simulation on the fly. Did you look into these kind of things?
So, building out, you know, on the fly. So perhaps the most, the closest example I have to tell you about is this potato kind of thing, right? What we have here is we have let's say a standard mesh that's doing finite element computation on a generic potato. And then we observe a new potato. We do optimal transport to transform that mesh to the new potato. and then run the finite element method on the new potato very quickly. So that adaptation can happen quickly. The tricky bit is, drilling and the rocks, the crack propagation, and a lot of that is very difficult to simulate. What we are doing then is using this, this idea of learning simulators one way or another through graph neural nets. At least it's fast enough. We're not trying to compete with people doing fluid simulators and super accurate simulation here. As I mentioned in one of the slides, right, we just need a useful simulator and fast.
Hi, great talk. Following up on the open questions session yesterday evening, do you have any insights on how you would go about simulating human behavior?
So in my example here, we essentially got rid of the humans, and I didn't want to do that experiment with the human and the truck, right? What I find interesting is that capturing a lot of human data and observing the multimodality of human behavior is an interesting way to do it. Whether we're simulating the sense of, how dynamics evolve and things like that, or whether we have an ensemble, like an implicit simulation of humans. That's perhaps a more interesting way for us to go. We log a lot of, behaviors, and we have an implicit distribution of human behaviors in there that we can then use for, for their own tasks. I think that's the best I could come up with, Jens.
So maybe the last question.
Hi, thank you, Fabio. I have a question follow-up. You say you don't want to build the best liquid simulator just enough for the task. Do you see any way of task-informed simulation? So having a simulator that is good enough for the task instead of having a simulator that is completely abstracted from the task. So if I need to grasp, it's going to be more accurate in the physics of the object that I need to grasp, but I don't need the physics of the background to be as accurate of that. That would be really like mind-blowing, I think. Do you think it's possible?
Yeah. So together with the QE masters of simulator, this guy here, Miles McLean, right, from Auckland, we are discussing this idea: can we have a simulator with a knob where we can say, okay, give me a fast and inaccurate simulator, now give me a slow and super accurate simulator, and I could tune that knob anywhere in this space to do it, right? I think this would be super cool if we can do it. We have some generic solutions to, let's say, looking at the solver itself and using things like, Fourier neural operators, and where the solver is embedded in there, we have a bit more flexibility to do it. But nothing at the moment that I would tell you, well, you can take that out of the box and apply directly to a robot, right? But having that simulation knob, speed, accuracy, is a really interesting area for us.
Thank you. We are out of time. Let's thank our speaker again.